Yeah, hello everybody. It's a pleasure to be here at the SUMO conference 24. My name is Andreas Freimann. I'm from the Fraunhofer Institute in Stuttgart. I'm working in the field of electromobility, energy and IoT, and this is Damir from the Esslingen University of Applied Sciences.
Yes.
Thank you. Well, our topic is the integration of topographical map information in SUMO to simulate realistic micromobility trips on hilly and steep terrains. Yeah. Now, if you look to the ground population worldwide, at the moment we have 2/3 of the world population lives in cities at the moment, and the number of automotive vehicles has increased a lot and is increasing at the moment, and causes some troubles such as noises, pollutions, and traffic jams. The topic micromobility is a very good alternative to the automotive vehicles, because it can reduce the private vehicles and can reduce the pollutions and all the troubles. Now, but we have a challenge in reference to the micromobility. It's the elevations. Micromobility gets challenging if there are altitude differences that have to become overcome over a trip. So if you go up a hill, you have to do that, and this causes an imbalance problems. So in the end, you will have some stations where are very overfilled and stations where are empty, and this implies that users cannot freely borrow or return vehicles anymore. And a second one is if you have electric vehicles for the micromobility, e-scooters, for example, you have an impact to the battery consumption if you have different altitudes. And this was the reason why we derived the requirement that these challenges need to be taken into account and needs to be further investigated based on a simulation. Well, this publication investigates micromobility for electric vehicles in combination with hilly and steep terrains, and we divided our publication into 3 parts. The third part is the definition of a workflow, which describes several steps to prepare a SUMO model, and part 2 it's the creation and the implementation of the workflow for the micromobility simulation, and part 3 is the validation of the simulation. Well, first of all, for the simulation, it's necessary to have a good map to present the altitudes, and we choose Stuttgart as an example. You see here on the right map the area of Stuttgart, and this part we choose that for the simulation because Stuttgart has very great characteristics. It has altitude differences of more than 300 meters, and Stuttgart lays on a sink at a height of around 240 meters, and there are very different valleys and with various lengths and different elevations. And you can see in this part here you have very high altitudes and low altitudes. Well, this is Stuttgart in real. We have here Stuttgart downtown here, down there, and where you have all the uphills here on the left side, on the right side, and here in the front here. Well, coming to the parts of our publication. First of all, part 1, the definition of the workflow. We divided it into 3 parts. The first part is the building the simulation model. Of course, we need to do that. And after that, we integrated the elevation data. And in the end, we integrated the micromobility stations. Well, coming to the first one.
So in the first part, we want to build the model, and we start, of course, with the OSM web wizard. And as we have seen yesterday, since we want to have also the bicycle lanes, we have to tick a checkbox for the bicycle. And then we get initial that file from the OSM web wizard. We have to also define another route file with the vehicle type definition. So for that, we define a bicycle V-class. That is, we restrict the vehicle type to only drive on the bicycle lanes. In order to track the electricity consumption over time, we have to define emission class as an energy unknown, and we also attach the battery device to it. That is, we define the model as an electric vehicle. So combining these two now, we get the initial SUMO model. And we then continue with integration of the elevation data.
Yeah, for the integration of the elevation data, SUMO provides the capability to process elevation data. However, the elevation, it's with the LE tag, you can integrate this one. But however, the elevation is used for prominent topological areas such as the mountain peaks. And if you want to have a realistic simulation, you need to fetch all the elevations for all geographical points. This is a very important thing, and it was a little challenging because we tried to find such elevation data. Normally you can get some shapefiles from the ArcView database, but it's sometimes registered, and it's you have to pay money for that, and it's not easy. So we tried to find an API, and we find a open topo data REST service to get the elevation data. You have to send a geographical point, and you will get the elevation data back in meters. We divided this process for the integration of the elevation data into 3 parts: the extraction itself, the integration, and the converting. The extraction, what we did is we used NetConvert to extract from the USM-Net file the plane files. It's very important because the plane files contain concrete information about the network topology and geometry. And after that, 2 files here are the files of interest: the plane edge, the edge XML, and the node XML. And the node XML file, you can see it here. All nodes have geographical points with an X and a Y normally, and the elevation data is added by a Z in the end. So you have in the end an X, Y, a Z. And the edge XML file has another one. It is structured within shapes, and one shape has several geographical points. It's the X1, Y1, and so on. And the elevation data is added by a Z. If just adding a Z attribute here to X1, Y1, and Z1, and so on. And after that, of the integration, we converted it back with the NetConvert to the OSM-Net file, and it was really great. We saw this here. You see a little extraction of the Stuttgart area. You can see the hills and all these attitudes that are inserted. Great. The next step.
So after integration of the elevation data, we also integrate micromobility stations into it. And there are also 2 ways to integrate micromobility stations. We can either use the OSM data, which is not complete. So for that reason, we use the GBFS, that is the general bike share feed specification data. So GBFS is inspired by the GTFS, and its main advantages are then that it has the up-to-date station data, and some providers provide sometimes also the real-time information. In case of the Regio Stuttgart, which we used, it's unfortunately not the case, but that could also be introduced. So, for example, one could use one could also extract the free bike JSON file and free bike station JSON file and also use that. So our process then consists only of reading the station information JSON, which contains the information about the station data, like its capacity, and the SUMO-Net file, which was created in the previous step. The station locations are then mapped to the SUMO edges, and the output file, it then creates an output XML file with the points of interest. So this then finishes the definition of the workflow.
Well, the second part, it was the creation of a scenario. We used we defined workflow and implemented all these steps and created a micromobility simulation scenario. And I will show it. It doesn't work. Okay, normally it should be a GIF. Driving around. Okay. Here you see the modeling here, and in the back you can see the goofy hilly stuff and the altitudes coming around, but it's just, it's not a GIF here, so it's not possible to see the movements. Yeah. Okay, the third part, validation.
So after creation of the scenario, we validate the scenario by creating at first a simple scenario where we create a micromobility trip between two docking stations which are in the hilly parts of the Stuttgart. So the route consists of has two elevated stations, and in the route there is a valley between them. So the lowest point is seen here in the middle at 276 meters, and the highest points, the most prominent points are at the end, and there is also a prominent point in the beginning. So this way we validate then the workflow by checking the attitude differences. We check whether whether the docking stations are available, and we also track the electricity consumption of the e-vehicle over time. And what we do then is we create two scenarios. In one scenario, we apply our workflow and add the elevation data to the scenario, and another one without elevation data. So what one can see is on the right side we have there two figures. In the left figure, there is the electricity consumption over time, and we can see there that in the scenario without elevation, the electricity consumption grows linearly over time, and that is completely unrealistic. Then the right figure, we can see elevation change over time. So as we expect, then in the scenario with elevation, with elevation data, in the downhill parts of the journey, the electricity consumption is reduced. Then as the slope increases and in the uphill parts of the journey, the electricity consumption increases significantly. So another thing also to note here is that since we use an e-bicycle, there is no recuperation. So the electricity consumption is never lower than 0. If there was a recuperation, we would see negative values here in the downward part. So this implies that the inclusion of elevation data is really important for micromobility and in general for any type of for any simulation. So what we did in the paper was we created a workflow for the inclusion of elevation data and docking station data into SUMO simulation models. We democratized access to the elevation data by using a REST API and reduced the initial hurdle to the inclusion of elevation data to the SUMO. And we validated the scenario using an e-bicycle vehicle type in a hilly area. And this brings me to the future work. And as a possible future work, so the limitations of the current approach can be separated into 4 key areas. So first, we should concentrate on more closely on the infrastructure. So bridges and tunnels are currently not modeled correctly. So when one has a bridge in the simulation, one would expect to get the elevation of the bridge and not of the river beneath the bridge, or of the tunnel and not the mountain peak above the tunnel. And this is currently the problem. So these infrastructure points have to be considered manually. Then the elevation feature could also be added to the OSM web wizard. But the problem currently is that there are limitations, request limitations, because the REST API which is used has a traffic limitation, so one can only call around 1,000 requests during the day, and it is currently only suitable for the smaller models. The third thing is the driving behavior. So with the different slopes, what we noticed is that when there is a slope in SUMO, and when we increase the slope, also when the slope is 80 degrees, for example, the vehicle is going to overcome it also, although it is impossible. And the second thing is the speed stays constant, only the electricity consumption increases. And the fourth part is building a tool, a complete workflow for the inclusion of the micromobility fleet scenarios into the SUMO. So our idea is to create a tool which could use the origin-destination tables, which one usually gets from the micromobility service providers, and to convert these into scenarios where we have the persons with the person plans where they can walk, ride, and then walk again, which would allow us then to simulate incentivization at the beginning of the booking of a micromobility vehicle, and then at the end of the booking of the micromobility vehicle. This would then allow us, for example, to research, to optimize the positions of the charging points, for example, within the city for the micromobility micromobility stations. And that's it. Thank you.